Okay, hi everybody. Welcome to Welcome to the world of innovative potential, and I'm your host Jordache. We're going to be doing another wheel tonight. Like we don't ever always do wheels, but we're doing the wheel of electronics tonight. Kind of got to fight for attention on myself here tonight because it's one of those subjects where it's like this is where I'm farthest removed. I'm like totally farthest removed here. You know, you play video games, you build computers, you do stuff like this all your life, but you really don't actually sit down and pay attention to like what you're actually doing and where it comes from, kind of thing. You kind of take it for granted a little bit, but at the same time, the guys who made this little sort of like tuning fork thing, I don't even know if I can get it in focus. It's that small. Hold on. Yeah, the guys who made this little tuning fork thing, they're insanely wealthy. If you know anything about electronics, it's part of the that's the socket pin from the male-female breadboarding sockets for used on used on PCB boards. I'm gonna go over some of this stuff right now. But what am I actually talking about here? Okay, so the electron from. Okay, hold on. So this kit I got from Amazon kind of walked me through all the bits and pieces, and it's from Freenove. It's got kind of everything you want and need in it, just to sort of get you familiarized and grounded with everything circa sort of 1975. More or less. We kind of talked about it in the last video, but this is more about like what I learned from this whole experience and sort of what I've sort of learned from my own life. So basically you're going from, with this wheel, you're going from the electro reduction tables in our electro reduction tables in electrochemistry, first year chemistry, where you have that chart on the thing that has like gold over silver over titanium over lead over antimony kind of thing, like, and they show the little different half reaction reduction potentials, and material, metal, and properties straight through to like, when you go around the whole history of it, then you end up with robotics. So there's a whole bunch. You have to keep a lot of like, here's the stuff in the earth in your mind, and then here's how we're refining it to get like automatons and robots and Tesla bots and deep blue mega computer kind of things, and the internet. So you kind of have to keep this in your mind for basically the last 150 years. Electronics sort of dominate more so than the Industrial Revolution. The Industrial Revolution does stuff, but electronics just kicks the shit out of everything for like the last century and a half and like forever into the future. There's some stuff that and like electronics isn't necessarily just like interface type of stuff. There's a lot of analog things that are still very much required and are still very much purpose design. Like an analog designer is far more robust than a digital designer from where I'm coming from, because I need this thing to work, and I need this thing to work without interruption. So that's kind of how just simple circuitry like this one here, just like a simple circuit like this with there's no mechanical moving parts. It's just like, here is a light bulb circuit. It goes on and it goes off. There's nothing more complicated than that. Is like your basic, super basic electricianship is still valuable, and it's kind of always going to be valuable, because you can build complexity over that, and that's sort of where the first computers came from. So that's sort of how I've broken this down. I've broken this wheel down into, there's connecting pieces for electronics. So it's kind of going like the wheel of cancer biology, but it's going from connecting pieces to processing pieces to sensing pieces, and then to like programming pieces of like modern electronics. So you can kind of go from like, you know, spinning copper wire for telegraph wires kind of thing, all the way to, no, we need 100 kilograms of spin wire for another Tesla coil or something. So that's sort of what's going on there with this. So basically you want to start with metal and material properties, and when you're thinking about design, or even when this kind of stuff comes up, lead versus tin, like different metals have different heat transfer coefficients, and this is important because you can blow out your circuits, or you cannot get an efficient circuit because you chose the wrong metal. Like when you buy stuff and you buy kits and you're doing your selections on Tiger Direct, on Tiger Direct or whatever your purchases are, the people building those products are already making these types of decisions for you. And a lot of the industrial standards were just like they were really sort of set in stone back in like almost 1900. It's just because the metal and the property or the material give the best results. That's why silicon is everywhere. That's why copper is everywhere. That's why, that's why it is the way it is. And if you want to understand it and start designing or using different things, metal materials and properties are at the forefront of your understanding. So you got to understand that for electronics. Solder and flux. These are they make wires stick together. Short of just like banging two sticks together to make an electrical contact. Solder and flux are kind of the two. They're your bread and butter. They're gonna make everything work. There's not too much to say here about it. There is a technique. Get one of the solder practice chips, where I got one of them, and it just sort of like gives you an appreciation of how much you want a microscope when you do some of the smaller stuff. But you can do it if you take your time and make it work. And you get a technique that's very sort of like I'm gonna say beautiful on this one, but it is very much like you're painting with metal if you do it right, and it's a very light touch. If you had a paintbrush, it would be like, you're using like like dots of ink to make electrical contact, and then sort of spot welding these things together. So soldering is an art form. Practice it, get used to it, do that breathing technique thing. Try and go for lead-free stuff now that it's available, particularly if it's one of your like main sort of jobs. It's like if it's the main function of your job, try and stay away from that. It's more like occupational health stuff. But solder is the glue that keeps electronics together, and you don't escape it anywhere. So wires and cables come up next. So basically, where solder and flux become, you can technically like do everything out of solder and flux. This is done out of just pure solder. This is a circuit made out of solder. Little octopus waiting to go there, but it is sort of like you can run wires and solder the wires together. And you can run cables, and they have their own, insulators. They have their own manufacturing. Like, they have their own system. They have their own categorical system. There's hundreds of wires from everything from your basic copper stuff You know, here's your basic insulated copper wire, all the way through to like Cat5 cables to your big, huge honking, like, you know, the wide world of wires, basically. It's a huge area, and I'm not really, and once again, I'm not taking forever on this stuff, just because they're old technologies. They've been here for, you know, since you started making wire threads, since it was, you know, gold was able to be like pulled and made into a thread, or just malleable, basically. So there's not much to say here. It's metallurgy. It hasn't really changed, because the metal itself, you might get new amalgams, you might get new sort of mixtures of metals, but for the most part, light glass was introduced. That was sort of the biggest. Glass wires, as fiber optics, was sort of the biggest thing, and that's something that's not really necessarily to be discounted in stuff in kits like this, where you could have a small fiber optic kit like that, like this. But it is one of those. It is one of those, like, that's probably the last big advancement in wire conduction, or types of wire that have come up, you know, in the past century. Resistors. Resistance is futile. No. I was like that one. Resistor. The fake gay flag, or the original gay flag, it has all the colors plus 3 extra, and this is what the resistor chart looks like. There's black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, and silver. Yeah, they help to bridge the electrical connection itself. They get in the way of the actual circuitry. So here's your wire, and it goes through the resistor, and the resistor comes out, and it's actually acting as a part of the wire. It's acting like a bottleneck in the wire system itself, to be able to slow down and give you a controlled output on the other side. So it's like having you turn on a faucet, but you're running it through a funnel, and only as much as the water as the funnel comes out, and that's sort of what the resistance is doing. It's controlling how much water is coming out of a faucet, in essence. But after the tap is running, so that's sort of there. So it's sort of been, you know, there's new ceramics to help dampen and get stuff, but this was pretty much well worked out in the you know, I want to say the 40s, maybe. There's lots of materials that do different dampeners, so it is one of those things where it's just like you might have new forms of resistor materials coming out that are either more green, environmentally friendly for manufacture, but this again, this resistor industry is pretty much set in stone. It's not going anywhere, and it's used everything. It's used everywhere. Even a light bulb needs a resistor. So they are everywhere. They're absolutely everywhere. And capacitors too. Capacitors are, here's my thing. Okay, I'm gonna get the other thing. So capacitors here are also helping to regulate electrical currents, and capacitors are the cylinder things. When you look at this little board here, I get that focus in. The resistors are these guys here. They're in the way of the electrical circuit, but these capacitors here, these two nubs here, right? These two nubs here, it's like a car front, but these two nubs here are capacitors. They control some of the voltage in I think it's an electrochemical. I don't know that much about it, but I know there's enough there that you're never going to escape them. it's one of those situations. Again, it goes back into like how back when they had light bulbs and computers and stuff, and like what do these materials do and why are these materials used, and capacitors and their applications in electrical circuits are there to sort of absorb some of the like extra electricity, if you want. They help to, they're like sponges. I put them in as sponges. They soak up extra electricity rather, because it's like it's not fair to the resistors that they just bottleneck everything, because then there's still overspill from the bottleneck. So if there is overspill from the bottleneck, you have these sponges there to soak up the electricity and mediate it through your electrical circuit. So that sort of gets, it's a stretch for me, because my focus is on the circuit itself, not on the components that make the circuit. But they're important. They're basically essential. Next are the semiconductors, and how the semiconductors are huge. They're huge, like you can have an entire wheel of this made out of just semiconductors. And it's more to the material and the behavior of the material itself that are sort of dictating a semiconductor, because it's a very general catch-all term for what the thing is. Like an LED, like if you look at Wikipedia, an LED is considered a semiconductor. The light-emitting diodes are considered a semiconductor, along with certain different types, like the NPN and the PNPs or something. The transistors there, they're there, and these are things that go in these are components, these are electrical components that go in the electrical circuit and then perform a function. Like everybody gets what an LED is, it's a light bulb, but there are other types of current regulating components for different types of electrical processes, different types of electrical motors, and these are the things that are setting up. So like this is the part like where I kind of shine here, where it's like specific to your case example, we don't know, or like the general case is the semiconductor, but specific to your example and what you want for your electrical circuit is basically I don't, it's not that I don't know, it's that you have to describe your electrical circuit purpose to say like, oh, well, we could put these different, we put these diodes in here, or we can add a transistor to help make your, thing not explode or catch fire. And then I included transducers here, just because they're kind of not thought of. It's more of, congratulations, you set your electrical system up, but transducers are important because they transfer different types of electrical signals to each other. They're acting like a bridge, not even a bridge. They're acting like a translator of electrical signal from one type of I'm gonna say this, but it's gonna be like wrong. From one type of electricity to another through just a linking circuit. Yeah. I don't know what type of like other examples there are in this. It becomes really I don't use a transducer, but I know that they're required, because basically what happens is it's like going from a mechanical input to an auditory input. and then back again, and not necessarily back again, but it's going from like analog to digital, and then from digital again back out to a different type of analog where you use your transducer. So in a way, it's sort of like the electrochemical cell is kind of like a transducer in this situation. It's like a chemical sensing it's complicated, its own thing. It's not even on, it's barely on this wheel. But the next big thing that kind of comes along here are these printed circuit boards. And these are a huge sort of step forward in the world, just because it's now like there's a manufacturability happening here, and you can put and then we're not even at computing yet. This is just still basic. This is still like 1940s. You're kind of seeing bits of computing power happening, but it's still very much like, this is my electrical circuit, and these are very complicated. They're still sort of, the world is still dealing with like very complicated electrical circuits and ways to manufacture complicated electrical circuits. And the PCB board comes along and allows for household electronics like a phone and or a radio to exist. So all of this kind of happens like a long time ago, but pull yourself forward to 2023. There's a factory that makes these custom for you if you use their design software. They'll make it for you within a week. Go see circuit maker, and then it kind of goes from there. So it's come like an insane amount of like distance. It's covered so much distance. It's ridiculous. So we're at printed circuit boards. They save you the hassle of doing the ferric chloride etching and putting down, it's very much what it sounds like. It's a board, and you can get YouTube videos on it, but basically it's a board, and you draw, your electrical circuit like with solder, right? Where is it? There you go. With solder, but it's more of like an electrical conductive thing. And then you just sort of etch it with, copper deposition and clean it off and do all this other stuff. It's like but the printed circuit board sort of paved the way to the arithmetic logic unit, and this is more where your actual computer kind of kicks in. This is where your and or not type of logic gates exist. And when this was developed, it kind of became the game changer, because it's now it's your first process. It's your first type of processor. So it's like taking a whole bunch of printed circuit boards that are going to do one type of calculation or one type of electricity, like, if this it's kind of like, if this voltage is this, you will have this light bulb turn on, but if it's this voltage, you will have this light bulb turn on. And you sit there and you record the output from someplace far away in the field, based on a temperature or something like that. So if it's too hot, if it's too hot, your light bulb will be this color. If it's not hot enough, it will be this color. And that's sort of like, you get like a sensor room at a factory displayed for your steam pressure sensors or something like that, right? So you're still kind of in these, you get these like industrial revolution type of steampunk situations where this is the first sort of arithmetic logic unit, where it's like, well, then we put another one after that, and you sort of daisy chain these little like if, and, or type of statements. And then you like run a century of this type of construction to create a microprocessor. So you get a whole bunch of these like little micro boards together with these two different conditioned light bulbs on it, and you put them on a big one, and then you shrink the big one, and that's where you end up with a microprocessor. So kind of what happens is you make some big gigantic computer, you make your electronics gigantic, and within a century they end up, you know, like underneath a wavelength of light, smaller than wavelengths of visible light. So that's kind of what happened with those ALUs and the microprocessors. And this is what's real. This is what's powering your computer. This is what turns your cell phone on. This is what makes your cell phone do its cell phone stuff. This is what makes your computer do its computer stuff. And that's really just kind of what's driving basically pretty much everything here. And then to make sure that it doesn't forget, read only and random access memory comes in. Random access memory was a Daft Punk album. It's a good place to start if you know absolutely nothing. Turn it on and start reading Wikipedia, because it will start to, you know, you kind of put two together. It helps you to remember what this is and what it does. Read-only memory is stuff like hard disk drives, CDs, compact discs, the old floppy drives, gigantic 8-inch A drives, printed on vinyl. There's a whole bunch of different forms of this type of memory, but basically it's allowing your computer or your processor to not have to start from absolute scratch every single time. There's been a lot of advancements in being able to read it up to like solid state drive. Like there's a whole bunch of stuff like solid state drives that are kind of now. You'll get into like crystal matrix drives if you kind of start reading into like the future omics of computing. But it's basically saying, well, here's a crystal of silicon, and we've managed to be able to read it with a laser beam, and, you know, have that be the entirety of the computer. We just shine a light bulb through it, and it, you know, the diffraction pattern gives us whatever data we want based on the rotation. Like you get like into these bizarre computational type of things where it's just these are different forms of computer. These are different forms of storing data. Are they practical? Who knows? Are they going to be commercialized? Probably yes, actually. But it's more to the it's more to the effect that these things exist in their multiple variant forms, but they're all kind of fulfilling the same function. It's just we're not able to integrate it with the mass production system we've already produced. So they're not really, it's like we have to buy a whole new form of computer, and we're not going to do that. Not until we absolutely have to. Because we've just gotten their costs down. But that kind of sort of brings me to the motherboard. So when you kind of put all of this stuff together, you end up with the motherboard. And the GPU, I might want to put GPU in there also. The graphics processing unit. There's like a CPU, a GPU, and the fan. There's other parts of the computer here too, like the modern gaming computer, but that's part and parcel of how much going from basically 1850 to 1985 kind of gets you here with this electronics wheel. When you put it all together, yeah, these industries, like, they grew fast and they grew hard because it was like non-stop production and it still is non-stop production for like a century and a half, almost 2 centuries. So the motherboard here is basically, it's holding your computer together. It's doing so many multiple microprocessors. There's like multiple microprocessors and the memory on the motherboard, and it just controls your computer. So like go look that type of stuff up. Um, but you don't need all of these things, but all of these recent things are setting you up to be able to have this conversation right now, or to be able to listen to this video right now. And that's just computing, but electronics is more than computing, and that's why I kind of jump into sensing here. So one of the biggest like enemies of the of the computer world is heat. So one of the first other forms of sensing electronics are the heat detectors, the thermistors, and they're small, and they go in the electrical circuit also, and they provide a capacity to basically read the temperature without being a thermometer. I'm sure there was a voltage-dependent mercury thermometer developed at one point to translate electrical potential into a registered thermometer. But since modern computing, it's a digital read. It is still kind of done that way, but it's a digital read without having to use any like physical, mercury or whatever. But heat is a big register on basically like all of your electrical components. You got fans in your computers specifically to dissipate the heat of the electronics, using the electricity and doing stuff with that information here. So this is basically kind of the most important one of the most important electrical sensors you can have, and that's your heat sensor. And then you use them for industrial applications down the road and stuff here. But basically, the sensing components that I kind of picked out are heat, chemical, pressure, sound, light, movement, and touch. There isn't really a particular order here, but these are sort of the main increases in complexity that I typically found from biology, and they're just sort of in like the order of biological evolution almost here, where it's just like, okay, if it's not hot, then it's corroded because you rusted. So now you have to like almost be like the rust on your wires because you got them wet from the humidity will cause a resistance change in your voltage outputs or stuff like that. So you do get into this type of like, well, now you have the promotion of a chemical detector. pH detectors are like this. They can work independently of processors, kind of thing. It's very much that that physical chemistry side of it. That's where this is kind of coming from here mostly, where it's just like, how do you turn a different type of signal into an electrical signal? How do you turn heat into an electrical signal? How do you turn sound, hello microphone, how do you turn sound vibrations into an electrical signal? A sound sensor is a microphone. A light sensor is it's a camera. It's a camera. Movement was interesting because it was kind of a little bit more like sound. You could do movement multiple ways. You can do movement through sound, and you can do movement through light. And they came in this handy kit from Freenove. Can I see it on the bottom here? Yeah, here. This one here is the sound detector. It has a sound pulse sonar. It's a sound pulse and a receptor that reads the distance. So there's lots of ways to have different types of movement sensors, and they're small too. So that's just sort of the things to just sort of keep in mind, that like There is so much here, and it's like it's not complicated. You know, it's just I'm gonna take it out. I'll whip it out for you. Okay, so this is an IR one. This is an IR detector. It's a type of movement detector, but it's in the infrared. It uses light to detect movement. And this is a sonar that detects movement using sound. So these come, 100 years after. These come 100 years after. Hello, I can see you. The upper glasses. No, but these come 100 years after the fact. And they're already like really like sort of miniaturized. And that's really the important draw here, is kind of realizing and understanding that it's still very, I don't want to say this, it's still kind of very rudimentary. It's just we've made stuff smaller. This is still rudimentary, but it's just had better manufacturing practices developed that makes its connectors flexible instead of being actual wires. So it's very... Yeah, it's overwhelming. It's going to take you a couple of days, if not a week, maybe 2 weeks to go through everything so that you understand the speed at which everything's sort of like, bam, here it is kind of thing. But it is still very much you're able to be caught up with it. You might not be designing, electronics for the kit manufacturer. But you at least get an idea of what the hell happened over the last century. Because it's not all like army stuff. It's like the stuff that made the tanks work is this stuff. The stuff that made the airplanes fly is this stuff. There's different gauges, like some of the air pressure sensors. So anyway, I'm getting ahead of myself, and I just want to like come back to just sort of the heat there. Sensing heat is important, and dissipating it's important also. There's so much. I'm gonna say from what I've seen, maybe like I was gonna be a little bit too generous there and say a third of the actual computing industry is like heat dissipation. When you get into like those like server rooms and stuff like that, it's like, yeah, when you kind of wrap your head around it, it is kind of like, yeah, a third of the computing industry is actually heat dissipation, because you now have to cool the computer down so that it doesn't like fuck up your components, or it stays optimal. So you're building massive air conditioning rooms for massive stretches of computer bays or of server bays and stuff like that. And it's like these huge air conditioning rooms, be able to run your casino kind of thing. So yeah, heat is. Don't underestimate heat. It's hot. What else do you want to say? Heat and corrosion. They're the two most. They will fuck you over so badly you won't understand how badly you're fucked with heat and corrosion. So with heat and then corrosion with the chemical stuff. So you want to be able to detect. It's like, well, are you in an environment? Are you operating in an industrial environment that is, caustic? Are my workers going to get killed on the job because of a hydrogen sulfide leak in the oil and gas industry? Or, you know what I mean? Like, it's very real here, and these are things that are important to have developed, and they very much are developed. So, chemical sensors go from wastewater for anywhere from, your ion detectors. So basically every ion has its own specific electrochemical detector sensor that you stick in the wastewater stream, and it gives you a concentration reading. So they're pretty much modified pH meters. They get a little bit more complicated depending on how much other ions or other species will interact with the endpoint detector. So it's like if you have sulfate versus sulfite, it'll be more of a difficult detection because nitrate and nitrate also interact with the same sort of electrode on this one. So basically these sensors are all just basically a wire and water reading the concentration, reading the electronic interactions of the stuff in it, basically. So remember in grade 9 when you put the zinc metal and the lead, you did those 4 metals, and that you put them in you put the zinc in the lead solution and it turned copper color, and you put the tin in the copper solution and nothing happened. That's sort of the basic of how these chemical sensors are sort of developed. It's basically a wire and water, and if there is your chemical of interest in the water, it will interact somehow or way with the wire, and then that produces an electrical potential or a signal that you can then read someplace else. That's what if we go to the thesis type of stuff, that's what linear sweep voltammetry is. We run a current from 0 to 5 volts or something, and when we start burning away your molecule in the water, it makes an increase in resistance. We read the resistance, and that resistance is proportional to its concentration. So that's how these things get calibrated and set up. So in the world of electronics, I'm somewhere in a chemical detector, chemical sensor area. Yeah, I fit in the chemical niche right here. Chemical sensing, really modified chemical sensing. Pressure sensors are kind of the same thing. You end up with like a little diaphragm and a membrane, or they have, depending what types of pressure sensors, because you can have, water pressure sensors, or you can have a physical sort of like spring sensor that if it gets compressed enough or flicked hard enough, it'll give you a voltage reading by creating electrical current on that one. So that's all in the kit there, but it's kind of nice to see where the hell in this industry are you kind of actually floating around here, because there are still there are sciences specifically dedicated to each of these things manufacturers. There are whole industries dedicated to just heat sink manufacture and the science and arts of heat sink manufacture for computers, and again for larger installations. So it never ends. Basically, it never ends. Sound is a microphone. You're able to, have wind vibrate a membrane. So this this moving piece of tape generates an electrical signal that is then read in an attunement to the waveform of my voice. Like, what the hell is that? But that's a microphone. Picks up a recording, and it scratches in the old wax gramophone roll. Exactly, that's how you record sound, or that's how you sense sound. Now you can get all crazy and go into those parabolic microphones and stuff like that, but that's basically sort of it. Light sensors, and I already I'm going to skip over movement and go to touch after this, but light sensors are photons. You're just getting a photon finding a photon in a certain wavelength to hit your sensor and generate an electrical charge that way. If a plant can do it, so can you. It's the basis for solar power, um, but that's um, again, that's its own. These are like when you think of a light sensor, a gigantic photovoltaic cell is a type of light sensor. It's not just sensing. It's actually, it's making more like it's a sensor geared to specifically harness light as a form of battery potential. So you're working a lot here with material properties on how to capture light better, crystal structures, and sort of that laser etched chromatography thing, diffractor I want to call it, but for optimization of the photon captures. But basically, if you can get a photon from a bright enough light source to hit your detector, it will excite the electrons in the detector to move some potential in proportionality to the energy of the wavelength. So red light, it generates less electricity than ultraviolet light. The end. That's basically it. Movement, you can use sound, wind, pressure, chemical, heat, unidirectional flow type of stuff. It could just be like a water wheel spinning in one direction, measuring the speed at which the water passes through, and that wheel generates an electric current, and you're done. You know what I mean? Stuff like that. But touch is a button. Touch is a button. Your touch screens, the sensors. Touch is using a type of pressure, but touch is more mechanical. Your keyboard is a type of touch sensing type of input for a computer. If I touch the case, nothing's hardwired to the case. But if I touch, if I push the F and J buttons to feel the bumps, you feel the bumps, and the computer starts typing and doing stuff. Hooray! Okay, here we go. So now we're into programming. So this is where it's like, oh, everyone went to school for programming, or we all do programming. Programming is incredibly manual. It's not even digital. This isn't even digital programming at this point. Programming is like generally like, well, how the fuck do you get any, like, this is a program. It does a certain thing with a certain output. Its whole purpose is self-contained within an analog PCB board. There is nothing digital about how this electrical circuit was programmed. Programming is getting the electronics to do what you want. So there's programming involved at your basic circuitry level. It's getting what you want. The way programming is used very commonly today is basically software engineering. Software engineering and programming kind of got like tied together because of just how many people are able to do it. And that's pretty much because computers got cheap enough to have in your household, computers are cheap enough for almost the per person level in an industrialized world. And that's all I kind of want to get about that is there is analog programming, and it still exists today. The Joey is basically analog programming. It's getting the battery to do. It's basically getting the battery to do what I want it to do, and how much of the battery I want it to do it in. So there you go. Programming, user interfaces. How does the person interact with the electrical circuit? That's what the user interface is. How am I interacting with this? I'm not actually interacting directly with the electrical circuit. So I have to make, I make a little box to put this in, and a light switch. I put a light switch on this electrical circuit to control it. The light switch itself, it is such a simple circuit. The entirety of the user interface is an on and off light switch. That's it. Turn it on, turn it off. On, off, on, off, on. You know, that's still very much today. Your light bulbs in your house are an on-off light switch. It's an on-off user interface, on-off. And then user interfaces get very complicated when you get into virtual environments. And you play your online video games, and there's your heads-up displays, and your UI and your heads-up display are all sort of integrated into the virtual environment and how you navigate that virtual environment. So it's just like it's one of those things where it's another one of those like century-long rabbit holes that isn't going anywhere, and it's just going to get more complicated or standardized and then more complicated. But the user interface is how you interact with the program, how you interact with the electrical circuit. So how I'm interacting with the electrical circuit inside of my computer is through the desktop configuration. So there is a screen showing me, but I also have the screen capture software here. So the virtual environment of the screen capture software, it is my user interface for this recording. You know what I mean? Like it just keeps like boom, boom, boom. Like it is kind of a little bit overwhelming, but it's only overwhelming in the sense that it's never had to be explained before, or you had to know the details of the minutia of it before, how to create it before. When you do have to know the minutia and how to create it before, it is mostly just sit down and I want you to do this. Sit down and then you make it do that. Sit down and then you do some other thing. And then you sit down and you do another thing again. So user interfaces and programming languages is sort of the next one. You touch your keyboard, you get a user interface, the light bulb turns to a different, letter or a color or something, and then it becomes a different programming language. So programming languages are just ways with which you're telling the computer how to do something, and it's an entirely interior. I'm going to call it. They're an entirely self-contained mechanism with which to describe an electrical circuit and a very complicated order of operations within an electrical circuit that have multiple floating operations or almost existential conditions within that organizational circuit. So like when you're way far removed at like the video game level of this, it's like, yeah, you're programming not only the movement of the character and the movement of the characters which interact with the main character, but you're also programming a set of conditions in which override, or exist and influence or force other determinants upon both the main character that the person is controlling and or interacting with, and the virtual characters. So the computer rules. So this is what makes it like the programming languages like so unique, is that they are custom tailored to different types of user interfaces. So if you're doing something like just on a website, it's going to have it. You're going to use something like Java or HTML or something like that, or Flash 5, or like the common internet programming ones. But if you're doing something more like a video game, you're using C or C++, or you're using like people get into Python, or like there's like 1,000 different programming languages, and they're almost custom tailored to what end result you're trying to create. Either just through the capacity, the complexity of the end result itself, or just just because it doesn't make sense to speak this language any other way. It's like you have the electronics do have a physical like capacity to them, and you have to make them make sense. So they are their own languages, and they're ways to tell jump way back over on the other side and get that printed circuit board with a microprocessor and a motherboard and a heat relay and all this other stuff to make a little dancing graphic guy dance on your video YouTube screen or something like that. So it's like 1,000 years worth of man hour and like 1 billion people tied into that one little dancing GIF on your Twitch stream. So I was like, yeah, that's where a billionaire comes from. Not the guy who made the dancing GIF, but the guy who had to program the programming language to be able to interact with a set of ones and zeros and a bunch of like silicon, resonator chips or pieces to even make that make sense. Okay, sure, why not? That's kind of where it doesn't make it's very difficult to make the last century make sense, because not only did you get you can understand the tech line going through, but when you have the tech line and then 8 billion people on top of that, it's just like your fucking mind explodes. It's just like white static noise sometimes. Because you're still trying to get how did 8 billion people come up with a dancing GIF on my YouTube stream or something, or on my Twitch stream? So that's sort of that's going from metal and materials all the way around right through the programming languages. The programming languages then lead into algorithms, because you can't really do anything with the algorithms. The algorithms are linked to the arithmetic logic unit because you can set them up. You can have an analog algorithm. It's like here, it's one of those Rube Goldberg machines is like an analog algorithm. You just set up a physical you put the marble here, and it does a whole bunch of other little things, and it loops around, and it does whatever, and it does something. That's one iteration of the algorithm. And then you do it 50 times, but if it loops twice, you have these conditions where if the algorithm loops twice, you now have 2 marbles going through, which then have a weight pressure sensor, which then divert it into a different situation. So you end up with that blue ball GIF on YTMND or whatever. Yeah, YTMND. You end up with the YTMND blue ball machine GIF. And it's there just basically here's all of these different possibilities that are all sort of calculated at the same time with these algorithms. And you go from a Fourier transform straight through to what the hell is making the next decision in AI. Did the AI build itself by purchasing parts on Amazon? A corporeal form, is there a PS5 with a robot body somewhere? Yeah, it's basically a Tesla bot. It purchased itself off of Amazon. It's like you end up with stuff like that. There's no limit to how complicated these things can get, particularly when they're hooked up with a virtual environment. So you can see how these interfaces and interactions at least are here are the steps. Here are the steps up the mountain kind of thing. So the virtual environments allow you to test things without actually having to interact with them in a physical manner in any way, shape, or form. You're still entirely localized within the hard drive of your computer now. But the virtual environments kind of don't, the closest virtual environment is an oscilloscope and Pong. And that's 1969-ish. 1960. Yeah, you're basically the year you landed on the moon. You got Pong. Um, so basically, your virtual environment is an oscilloscope originally, and now you just have like fully functioning, micro screens. You have virtual. I have a virtual camera in this recording, in the OBS recording studio here. So that's just sort of like, okay, well, that's more in the last decade than in the last century. But in 1975, you end up with the virtual environments. They're interacting with something, but they're mainly maintained within the hardware itself. They're running calculations in the background. This is sort of what your operating system is kind of living off of, and at the BIOS level kind of thing. And then robotics, because you can't do any of that without robotics, because how are the robots going to make decisions internal to their robotistry? There's more to robotics here, because you're like, if you're going for the automaton, like you go from basic simple, you go from pulley and lever automatons from like the 17th century kind of thing, straight through to a Tesla bot, and then you go beyond a Tesla bot to what I want is basically a personality robot. It's basically is running its AI, mimicking decision making and personality type of considerations or talkings and the background noises of the person, of the human being. There's no way you're doing that in an analog system. The analog system is going to be the size of an elephant, without a virtual environment on board, without an algorithm on board, without these like pre-distinguished subroutines being able to sort of say, oh no, under this condition, and I'm hungry also, I do this, or under this condition and these people are involved, I can't do this because there's a pre-existing hierarchy there that would cause a conflict. Or you end up with these like whole like bunches of personal nuances in decision making that robots still kind of don't do to be sociable. So like there's this whole like virtual environment of social decision making that's going into your robot just so that it can do this. But also your robot would need all of the sensors to be installed in it also. So you need touch, you need touch, you need sight, you need sound, you need chemical detectors, you need light detectors, you need movement detectors, you need wind detectors, you need pressure detectors. There's temperature detector. Well, he's kind of tying up temperature here also as like hot and cold, presence, absence. In addition to its servo pressure, every servo motor on your robot has to be able to understand how much force it's exerting through some type of like feedback loop. So every servo motor has, every joint on your robot needs a gyroscope and a pressure feedback monitor, and you're making these like you have to make these types of like joint patches so it doesn't fall over, or or it's useless, or it's worthless. It's not impossible, but you end up with a situation like Tesla where it's like, well, nobody's ever made like a fully functioning automaton before, and so there are no parts in production for any type of facsimile for what's actually required for this robot. So poor Elon Musk is stuck with slave of the world here. He's stuck with the challenge of building an entire industrial supply line for something that people are scared shitless of. In truth, or they're too poor to afford, or the whole corporation is just like, well, I don't want a humanoid robot. I just want an arm that does this. Well, we got a whole bunch of this, but it's just like, you know, I kind of feel bad for it. Like, not bad for him, but it's like, there's probably a cheaper solution than building the entire thing. Oh, give your robot balls or a pair of tits, because those extra gyroscopes are how the programmers understand everything. So your robot should understand everything that way too. Yeah, it's a lot easier said than done, but basically if you're trying to build like anything, you build everything from the ground up from scratch. And keep building, I suppose. And then that sends you back to metal and material properties, because the only way those fucking robots are going to be profitable if you send them back into the mine shaft to dig out another robot. And I'm not even like, I'm laughing, but that's not even like the joke on it, because those types of like you need the robot to go back into the mine. You need the robot to go into outer space to be able to get those minerals to build more robots to make the first robot actually profitable. And that's kind of what happened in the last, century and a half of steel manufacture. Once you got, your steel blast furnaces up and running, and okay, we can burn, we figured out what the hell is in crude oil, and now we can, you really get this you get this industrial line started. So now it's like we're 150 years into oil and gas production with oil, gas, steel, and oil, gas, steel, and electronics, and then plastics come in halfway through. So we haven't even had that's kind of where we're just basically stopping here, because by 1975, you get so many problems from the plastics and pharmaceuticals that come out of oil and gas, plus the oil and gas pollution in and of themselves. Most major governments that are involved in this just basically say no, just basically shut down. A lot of their they created the EPA, Environmental Protection Agency, and the Food and Drug Administration because there were problems in the 50s they were finding, and it's been like a hawk, just watch like a hawk, like laser beams, kind of just holding on to everything here, because it is really just extremely heavily innovative regulation. You literally have a dictator in charge of the regulatory industry, because if you don't, 1 million people a year die for no fucking reason, or for a really stupid reason. So that's sort of why those laws are there. Why dictator, DICKTATER, why dictator is in charge of all of these regulation organizations, is because if those rules aren't really stringently enforced, a lot of people really get affected really hardly. There's huge consequences for bad regulation. Yeah, so mining robots, and you're back to metal and metal properties, and we're done for the hour. Okay. Hooray! Oh, just untwist that. You can just pull it out of your brain almost. And that's basically electronics. So this is good. This is good enough to go. Take this. Go. It's up on the website. Take this. Go into Wikipedia. Go into learning what this is, because you're gonna sort of take this and then go into your component purchasing and component creation tools like Circuit Maker, and you're still going to need to know how to navigate with the plethora of, and I hate when they call this ecosystem, because they're going for artificial life here, but each component has its own I fucking hate that ness about it. It's you know what, the automaton, you want to make the automaton a new species, give it species rights, get your shit together first. Okay, that's kind of the thing here. I don't like ecological terms for industrial terms. It devalues the ecology. Because you're not bringing you're not bringing biology terms and protein terms into the electronics world. To get the full understanding. So it's like, there are 3 proton counters in nature. Your DNA synthase from the CGAT bond, there's a proton missing. GCAT, your DNA is synthesized by counting protons. The presence or absence of a proton on your GCAT base pairs. The whole enzyme apparatus is electrically generating or conductive based on the presence or absence of a proton, a missing proton in GCAT. The second one is the same thing happens with the RNA molecule when you're doing your transferred your tRNAs to make synthesized proteins. Again with the GCAT and GCow, and then your DNA, not DNA polymerase, your the mitochondrial one, the proton pump. ATP synthase. So ATP synthase is also counting protons. So there's 3 instances of counting protons in your biology factor, and they're all binary computers. It's either the proton is either there or it isn't. When you synthesize DNA, the proton is either there or it isn't when you're synthesizing proteins. And the proton is either there or it isn't when you're synthesizing energy to run the whole fucking system. So, with that left in storage, I'm just gonna switch you over back to the world of innovative potential. Remember to back up and shut her down.